As with many other subjects in physics, the standard units for mass are a bit cumbersome at the nuclear scale. 1 kilogram is 1,000 grams, but even a gram would be a large unit for nuclei. 1 gram of hydrogen contains 1 Avogadro's number of hydrogen atoms. That's 6.0221415 by 10 to the 23 atoms. The number comes from realizing that gases combine in integer amounts to form molecules, and is also tied into a lot of interesting and a bit complicated chemistry. So I'll skip it for now. I will deal with it in more detail when talking about thermal physics and ideal gases in other podcasts. For now, we can establish a system of showing masses of nuclei in a more meaningful way. 1 gram of a substance contains 6.0221415 by 10 to the 23 atoms worth of material. Therefore, 1 atom weighs 1 gram divided by 6.0221415 by 10 to the 23. This is the atomic mass unit. It is the same as 1.66054 by 10 to the minus 24 grams, or 1.66 by 10 to the 1.66054 by 10 to the minus 27 kilograms, only slightly smaller than the quoted mass of a proton. So instead of saying that a proton has a mass of 1.67262178 by 10 to the minus 27 kilograms, which is a big mouthful, we can now say that a proton is about 1.007-ish atomic mass units, or 1.007 U's. Much easier and without the standard notation. Of course, we live in a world with special relativity, so we aren't simply limited to quoting masses to people. We can give their energy equivalents. Instead of saying that an object has 1 U of mass, we can say that it has 931.3 mega-electron-volts of energy instead. Take the mass, in kilograms, times it by the speed of light squared in meters per second, divide all of that by 1.6 by 10 to the minus 19, and that will give you the energy in electron volts. Divide it further by 1,000,000, and you get the value in mega-electron volts. I've given the value quoted by the exam board, here 931.3 mega-electron volts, which is slightly different to the value you get if you use the numbers above. It's also different to the number quoted on Wikipedia, but all the differences are small, and they can all be put down to rounding errors where you decide to draw a line at the decimal place. Why would we want to quote mass as an energy? Well, you see, it turns out that energy is much more relevant when you are trying to investigate the nuclear and subnuclear world. In Europe, we have a huge particle accelerator called the Large Hadron Collider. It smashes protons together to see what falls out. However, if you smash protons together at different speeds, you'll see different things. It's not because the proton contains anything other than 2 up quarks and a down quark. It's just that the energy made in the smashing of the protons can be used to make other particles. The LHC has beams of 4 tera-electron volts each, making a combined power of 8 tera-electron volts when smashed together. A tera-electron volt seems like a huge amount of energy, and in particle physics terms it is. But in everyday terms, these beams have less than 1/1,000,000th of the power of a light bulb. However, 8 tera-electron volts is about the same energy equivalent as 8,000 proton masses, and in particle physics, a proton is pretty heavy. As mass and energy are equivalent, and everything else is in energy terms, why bother changing it back to a mass when it makes just as much sense as an energy?